Hello, everyone. My name is Kelly Dudley, and I'm with the New Center, and I'd like to welcome you to today's webinar entitled The New Low Carbon Concrete Materials Guide Overview. And so we're glad you could join us today. A video recording and PDF of the presentation you're about to see will be uploaded to the new website, newconcrete.org, following today's webinar. Attendees are in listen-only mode. You will have an opportunity to ask questions in the Q&A dialog box at the end of this presentation. Okay, quick disclaimer. The ideas expressed in the following presentation are those of the speaker and do not necessarily reflect the views of the New Center, ACI, or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixture components, among other things. You should consult your materials, cement, and concrete professionals for design assistance. Nothing contained herein shall be considered or construed as a warranty or guarantee, either expressed or implied, including any warranty of fitness for a particular purpose. Okay, now I'd like to introduce you to News Executive Director and eventually News Technical Director. Thank you.
Hi, everyone. Thank you for joining the webinar today. My name is Carrie Sutton, and I'm the Executive Director for New, and I just wanted to welcome you to the webinar and just publicly acknowledge the hard work of Mary and Sarika on this guide. It was a big effort, and we hope you enjoy the webinar today. So Sarika, you want to go ahead and introduce yourself?
Hello, everyone, and welcome. My name is Sureka Sumanasuriya. I serve as the Technical Director for NEO. Thanks again for joining us today. I think without further ado, I would like to introduce Mary Christiansen, today's speaker. She's the author of this guide. So Dr. Mary Christiansen is an associate professor in the Department of Civil Environmental Engineering at the University of Minnesota, Duluth. She earned her BS and MS degrees in architectural and structural engineering from the Milwaukee School of Engineering in 2008, and her Ph.D. in civil engineering from Michigan Technological University in 2013. Dr. Christiansen teaches courses in concrete materials, structural design, and sustainability. Her research focuses on the development and characterization of low-carbon concrete and the high-performance materials aimed at improving the sustainability and resiliency of concrete infrastructure. She was the founding chair of ACI Committee 242, Alternative Cements, and is a member of ACI Committee 232, Fly Ash in Concrete, and 240, Porcelains. Mary, please go ahead. Thank you.
Thank you, Sarika, Carrie, Kelly. Appreciate it. I'm really excited to be here today to discuss this project that, as Sarika and Carrie mentioned, has been going on for quite some time. All right, I wanted to start out by just talking about sort of how this guide came to be and what the purpose of it is, and with the hopes that that will help it make sense as to how it's organized. So the purpose of the guide largely started as just sort of a small little document that would go over what are some of the low carbon concrete materials out there. And as we started to write that, we started to talk about and say, well, it would be really useful if there was sort of an overview of the baseline traditional Portland cement concrete. So we added that. And then as we started to talk about global warming potential and embodied carbon, we started to say, well, we should explain what those things are. And so it just really has sort of blown up into a much larger document. And what we ended up kind of going for was to create a document that sort of has a full view of the low carbon content, EPD, fly ash, slag, just all the different words that you hear around, concepts that you hear around, and we tried to just organize them in a way that kind of a one-stop shop, whether you're new to low carbon materials or whether you've been dealing with concrete materials for a long time, or you're just new to concrete altogether. We wanted to make it an accessible document for a variety of audiences, somewhere where you can come and you can just see where all these different pieces plug in to the larger scope of low carbon concrete. And so, like I said, I always tell my students half the battle learning anything new is learning the vocabulary, right? And so we tried to just really include as much of that as we could. And Sarika and I had a whole lot of different conversations about things that honestly have confused us over the years. And so we really tried to dig into those things in particular and organize them and sort of explain them. And all this being said, there are so many other amazing documents and references and guides and things out there. And so I definitely hope that you will explore those as well. We just wanted this to be sort of a central, go here, get the big picture, read the references, go somewhere else and get more detail. And then the other thing we wanted to do was, of course, to present some of these low carbon concrete materials in context. So what's used today, what's coming, down the pipe, and then what's sort of still in the lab being experimented upon. Excuse me. So with that, I'm gonna go through sort of how the guide is organized, and I'll go through chapter by chapter, which sounds very exciting, I'm sure, but I'll try to make it fun. So as I said, we really wanted to include a baseline of information that if you're new to concrete or if you're new to low carbon concrete, what are the tools and the things that you need to understand in order to understand how to use and implement these other low carbon options. So that's what the first part is about. Part 2 explores low carbon alternatives to Portland cement specifically, so the binder, and I'll explain why that gets its own part in a moment. Part 3 looks at alternatives to non-binder concrete materials, so namely aggregate reinforcement and water. And then part 4 does talk a bit about design strategies and mixed design, though that is not the topic of the book. We felt it would be remiss to not talk about the importance of mixture proportioning and design that goes hand in hand with material selection. All right, so part 1, understanding the carbon footprint of concrete. So you might be sitting there thinking, like many people are, what is the deal with all the carbon emissions associated with concrete, right? We see 7 to 8% global annual carbon emissions. We see 5 to 8, 6 to 8, 6 to 9, depending on what your source is. But we see that it's fairly significant, right? And so there's a lot of sort of people out there that are like, what is the deal? And so the purpose of this whole part of this first part of the book or the guide was to try and dig down and say, where is that carbon actually coming from? And that will help us later kind of target where should we put our efforts. So one thing that's confusing is I think that the carbon industry, there's a lot of talk about, the carbon footprint or the embodied carbon, which is the carbon that goes into producing cement or concrete. They say it's responsible for all of this global anthropogenic CO2. And then you look at charts like this, where we have emissions on the y-axis. So this is kilograms of CO2, you could just say, per kilogram of material, and then energy on the x-axis. And you look at this compared to steel, aluminum, and I'm not throwing those under the bus at all, but concrete and cement are a little bit lower. And so you might say, well, why, what's the big deal? Well, the big deal is that we make a lot of cement, okay? We make a lot of concrete every year. And so this is looking at Portland cement production from the 70s until today, or close to. And you can see there was a pretty significant hike. There's been a bit of a plateau over the last decade, but projections are that production is going to continue to increase, okay? And so you have to consider two things. One is the carbon density of the material, right? And so if you look at this, you see cement is around 1 kilogram excuse me, of CO2 per kilogram of material. And then you compare it, you double that or compound that with the fact that we are making an enormous amount of this material every year. And so that's what accounts for those really high emissions, okay? So now if we dig in a little bit deeper into concrete, what is concrete? Well, it's Portland cement, water, air, of course, crushed aggregate, and river sand. So you could just say fine aggregate, coarse aggregate, you could say sand and rock, okay? At its most basic, this is what it is. And you can see that about 3/4 of it is aggregate, and then there's like a 2-to-1 ratio of cement and water, okay? Well, it turns out that even though the cement takes up kind of a small amount of material within the whole of concrete, look how much embodied carbon from the whole mixture comes just from Portland cement. Okay, and so this is a way to look at it and say, well, where should we put our efforts? Well, probably we should put our efforts toward that Portland cement, which has which is carbon dense, as you could say. So this is just showing kilograms of CO2 equivalent, which I'll explain in a moment, actually, per kilogram of material, but you can say 1 kilogram of cement 1 kilogram of water, 1 kilogram of sand, 1 kilogram of rock. So this is sort of, explaining, okay, so it's the Portland cement we really need to zoom in on. So the second chapter is traditionally produced Portland cement concrete. And so we zoom in and we say, okay, this is our baseline. Traditional Portland cement concrete is what's most often used around the world. And so let's offer a good explanation of how does it work? How is the cement produced? What happens when you add water to the cement? And when you have an understanding of that, then when you start to include these other materials, then the changes and the differences start to make more sense. So that was the goal here. And we have a really cool picture of a cement plant in the US from Jeff Hook. Thank you, Jeff. So we have, just to give you a little orientation if you're not familiar, a little bit of storage here. This is what we call the preheater or precalciner tower. And so the raw materials like limestone, clay, shale go up into here. And then they come down through the tower and hot air goes up. They start to heat up. And then they get to this thing right here, which is the kiln, okay? And that's a long cylindrical thing, cone or cylinder with a flame at the bottom, okay? And so they slowly go through the kiln, a whole bunch of chemical reactions happen, and eventually these raw materials turn into clinker. And so clinker is what comes out of the kiln. Now the clinker is cooled down really, really quickly, and then it's ground together with gypsum, and then you get Portland cement, which of course is the gray powder we're all familiar with, okay? So chapter 2 goes through this procedure, kind of explains, all of the technology and the vocabulary. And in particular, we look at, again, here's just sort of another diagram of what that process looks like. But we look at the first steps, right, are to quarry the raw materials, crush them, process them. Here's the kiln and preheater tower, and then cool, etc. But you can see that the bulk of the energy and the carbon produced comes from the kiln and the preheater. And so if we zoom in further on that point, because again, we're trying to understand where does this carbon come from. So here's a cool picture inside a kiln from Larry Rowland. Thank you, Larry. And this shows, I don't know if you can tell, but it is very, very hot in there, okay? And so what happens is those raw materials come through, they come into the kiln, and limestone is one of the main raw materials to make Portland cement. Calcium carbonate is the chemical formula for limestone, CaCO3. And it turns out when you heat up calcium carbonate, you break it apart into lime, which is what we need to make the cement, and CO2. So here's that carbon, some of it, okay? The other part comes from, well, how do you get this flame to be so hot? You need fuel, right? And so combustion from fuel accounts for a large part of the rest. So here's a breakdown looking at, this is 0 to 100%. This is that 7 to 8% global anthropogenic CO2 we're talking about, or a big chunk of it. And you can see the green in the green here, 50% roughly, give or take. You could ask 100 people and get different numbers, but they're pretty close, are going to be from calcination, okay? That reaction where the calcium carbonate is heated up, broken into calcium oxide and CO2. And then about 40% comes from fossil fuel consumption, or combustion, in the kiln. And then 10% comes from electricity or transportation, okay? And so I think it's useful when you're trying to look at low carbon concrete to understand where does that carbon come from and what changes can you make to reduce that carbon that's coming out. Chapter 2, I have to keep myself back on track for the chapters here, not get into teaching mode. I apologize if I do. But chapter 2 also includes an overview of hydration, right? So that's when the cement in gray here mixes with the water in blue here to form, concrete, these phases that make the concrete hard. And we go through a bit of the chemistry. We tried to keep it very palatable in that chapter, but enough so that you could understand how alternative cements or other materials that do alter the chemistry, how they differ. Chapter 3 of part 1 goes through this concept of life cycle carbon thinking or life cycle thinking. So when we look at concrete or concrete materials, often we really focus on this first part of the life of a material. So this is sort of like, you can think of this as like, this is time from left to right. So this is sort of like getting the raw materials from the ground, transporting them to the cement plant, making the cement, making the concrete, producing the concrete and constructing the project, the construction stage. And then the use stage is when that building or that bridge or that whatever is in use, right? And so there are carbon emissions associated with that because you got to fix things, you got to replace things. And then at the end of life, you got to tear it down, you got to destroy it. Well, just tear it down or recycle it or transport it or whatever, you got to dispose of it. And so there's carbon emissions associated with this whole life. And then sometimes you can reuse or recover at the end, which is awesome. But What we want to do is get away from just looking at this early part, because as it turns out, this early part is where the bulk of the emissions come from when it comes to material production. That makes sense, right? I mean, especially in cement, in the case of cement, where we look at what's happening in the kiln. So what we want to do is definitely still focus on that and acknowledge that that is significant, but also look downstream and say, is there anything we can do here in our material selection, or maybe even mixed design or proportioning, that can save us some carbon later, okay? And so we want to look at whole life carbon. So just as an example, embodied carbon, okay, we might say, I'm going to take my Portland cement, I'm going to replace it with some fly ash or some slag or some supplementary cementitious materials, which I'll talk about in a moment. And so we're able to reduce the embodied carbon, that carbon that's in that very first part of production, okay, and that's awesome. But we get a bonus when we do some of these changes that allow the concrete, for example, to be more durable. So if you thoughtfully put in SCMs, you might end up with a more durable concrete. And so downstream, you can save carbon because you've got a more resilient structure, a structure that does not require as much repair or rehabilitation or even replacement. And so just part of chapter 3 is just trying to help get that into your head, kind of let's look at the big picture, let's think ahead, make decisions now that will impact us later. We also go through a whole lot of vocabulary. So one of the things that is talked about a lot, and a driver of a lot of this work is climate change, right? Or global warming. And so if you're not familiar, here we are on the earth, right? And here's the sun. The sun heats up the earth, and we are here on the earth living our lives, and we drive our cars and we heat our homes and everything. And we emit, we make cement, right? We cause greenhouse gases such as CO2, N2O, CH4, which is methane, to go up into the atmosphere. And they get kind of stuck there, and they kind of create this blanket around the earth. So then when the sun comes in, it bounces off the earth and it gets stuck in that little blanket, and then it comes back down again and we start to warm up. Okay. And so that's where, if you think about global or climate change, or excuse me, global warming, it's sort of like a greenhouse, right? Greenhouse gases. It's sort of like a greenhouse. We start to warm up. So it's pretty complicated because these are only 3 greenhouse gases. There's many others, and every different process and product we make creates greenhouse gases. So what we do, this is just an example of what's in chapter 3, but what we do is we normalize all these gases to CO2. So when you saw earlier, I said CO2e or CO2 equivalent, that's what I mean. So we say essentially 2 kilograms of methane is equal to 50 kilograms of CO2. So then we can add all the CO2s together and we can just talk about carbon. And the reason we use carbon is because it's the most common greenhouse gas. So just a little tidbit, but that's the kind of stuff that we tried to put into chapter 3 to help understand, why do we always talk about carbon. The other thing in chapter 3 is we talk about EPDs, which are environmental product declarations. So for example, this is from Athena's Sustainable Materials Institute and ASTM. Thank you to them. This is a EPD, which is a document that sort of gives what is the environmental impact from a third party of the production of your material. So this is for Portland cement. And so you can see global warming potential, GWP, is 919 kilograms of CO2 equivalent, which we just talked about, per metric ton of Portland cement. And so this is a way for us to kind of quickly and easily say, what is the environmental impact of these materials that we're considering? And the reason that we talk about EPDs and LCAs, and I won't go into all those, but they're all in the chapter, is because we need those in order to quantify and say, are we achieving low carbon concrete, right? Because you can kind of say, theoretically you are, but it's really better if you can sort of get some numbers behind that and some data, right? And so these EPDs are super helpful there. And then we also mentioned a little bit about the ACI code 323, which just came out 2 years ago, I know, or 24, however long that was ago. And this is a really cool, big step, I think, toward helping industry and engineers to start to really consider what goes into the concrete mixture instead of just how strong it is. And so this is a really good method for doing that. And we're hoping that this guide will help kind of provide some of the background information for that low carbon concrete code. Chapter 4 of part 1 goes into the concept that whenever you're doing something like material selection, there are so many things to consider. So if you take, for example, sustainability, I think people are pretty familiar with the three-legged stool, where you say something is sustainable if it's considered, if you have considered the environment, society, economy, right? We added resiliency to this as well. And what we did is we sort of expanded that to say, there's just all these things you really need to consider in addition to what the carbon footprint or the embodied carbon of your material is. So when you're selecting materials, you got to say, how much does it cost? What's the constructability like? Does it change? Do you need to retrain your labor force? How available is the material, right? What's the performance? Of course. What kind of regulatory standards and compliance needs to be considered? And so we just wanted to include sort of all of those things in chapter 4. And we also went through and sort of summarize a lot of the documents that you see. So ASTM material specifications versus ACI codes versus RILEM documents, and tried to kind of just give an idea of what those all are, because there's so many of them, which is great and awesome, but they can get kind of confusing. All right, so that was part 1. So, my advice to you would be is if any of that was, stuff you've never heard of or stuff you're like still a little bit confused on, definitely check out part 1. If you were like, yeah, I already know everything in part 1, jump to part 2. So part 2 focuses just on what are the low carbon alternatives to Portland cement. And the reason for that is because, as we showed earlier, that's where the bulk of the carbon emissions are. So for parts 2 and 3 of this document, we developed what we called readiness levels. And we said, and the basis behind this was not at all to judge materials or to say this is better than that. 0, we did not consider that at all. What we wanted to do was to show people that are new to the industry or new to low carbon materials, what's been used a lot in the past, or what is currently being used now, what is really starting to be used a lot, but hasn't really doesn't have the historical performance data maybe of some of these other materials, and then what are materials that are just really, they're kind of still in the lab. Boy, they seem awesome, interesting, but they're still at the lab level, or they haven't been scaled up yet. And so we gave most of the materials sort of a designation of proven, emerging, or experimental, and probably you could survey 100 different concrete people and they would give you a whole different, they would put materials in different categories. We did our best, and we, definitely will keep updating that as things change, with the hope that lots of things can come up into the proven level. Okay, so part 2, like I said, is about strategies for reducing the carbon footprint of the binder. So we broke this down into 3 sort of general thrusts, I guess you could say. The first one here on the left is to use SCMs, supplementary cementitious materials, or mineral fillers during batching to replace some of the Portland cement. Okay, so we already know that the Portland cement has a pretty carbon dense, right? Meaning you release a lot of carbon to produce it. And so the first option is to say, well, let's just get rid of some of that cement and put in another material. So SCMs and mineral fillers are our options, and we have a chapter on each of those, which I'll go over in a moment. The second option, excuse me, the second option is one that we actually don't have as much control over as you might think. So the second option is sort of considering that at the cement plant, the folks that are running those cement plants, there are levers they can pull to reduce the carbon emissions during production of typical Portland cement concrete. And we'll go through that in a moment. But essentially, this is sort of where maybe your buying power would come into play, where you could look at an EPD, for example, and say, what is the GWP? What is that carbon? What are those carbon emissions from Portland cement? And you could potentially choose one with a lower GWP, if that company were to be making efforts to reduce it. And then there's also within that sort of category, blended cements, which I'll talk about. The third sort of bin we put binder options into is to just scrap Portland cement altogether and adopt a whole new alternative cement. There's a whole bunch of them out there, and they are a whole new wild west world. They have different chemistries, different performance. Sometimes they need different tests to analyze them, but they can achieve some pretty amazing things. So this is sort of how we organized just the idea of what do you do, how do you sort of address the carbon density of the Portland cement. All right, so chapter 6 is all about supplementary cementitious materials, and it ended up being a pretty big chapter because we wanted to just kind of give an overview of all these different types of materials that can be used as SCMs. And what's available to you regionally plays a big role. So some of these materials are available in some areas and sometimes they're not. And so the first part of chapter 6 kind of goes through what are the physical and chemical characteristics that you should consider when you are looking at an SCM to possibly use. So an SCM is a material that replaces some of the Portland cement in your mixture, and it actually chemically reacts with the Portland cement that's remaining and the water, and you get this really nice pozzolanic reaction, which I didn't go into in this presentation, but it's really a kind of a beautiful system. So sorry, I have a dog in there barking, sorry. I was hoping they wouldn't. So we broke the supplementary cementitious materials, SCMs, into 3 main categories. So we have industrial byproducts. So those are the classic fly ash, slag, silica fume, ground glass, etc. And you can see the colors here are sort of back to that proven, emerging, experimental. And then we have natural pozzolans, which we broke further down into calcine clays and shales, volcanic materials, and siliceous sedimentary rocks. And so you can see here, some calcine clay was used to make this dam out west. The Colosseum, of course, used volcanic ash, which would be considered a natural pozzolan. And then we can have a section on biomass ashes. So rice husk, sugarcane, palm oil, fuel. So that's the refuse sort of from those materials that if it's burned under the right conditions can create a really nice pozzolan or SCM. So those are the ones we went through. And for each of those, we tried to go through what is it? How is it made? What's the composition? What are the physical characteristics? Is there an ASTM spec or other AASHTO spec? How does it affect fresh performance and hardened properties, a little bit on availability. And for so many of these materials, there are full reports from ACI and other organizations, of course, that go really into details. But we just, again, wanted to sort of show an overview of all these materials. And so that's what we provided for most of all of these. And there's more information provided on the proven and emerging than there is on experimental, largely because in some cases it's just not available. Okay, one thing to note about SCMs, and here's just a picture of a bunch of them, silica fume, you got slag, a bunch of fly ashes. This is about exciting as they get because there's a bunch of powders. But one thing to consider is that I hear a lot of people, I think, get confused and they say, oh, all SCMs are the same. You can just put however much in you want. Well, it turns out they're very different, right? And so we tried to include a lot of graphs such as this one. And this isn't an exhaustive list of all the materials we covered, but it's a bunch of them where we kind of show what's the typical replacement level. So the blue or the green, the color part is sort of what that typical replacement level is. And then this hatched color later is sort of stuff that's sort of some replacement levels that have been explored higher than or what is typical. And so you can see silica fume, boy, you know, you only use like a 5 to 10% replacement, whereas Class F ash maybe you can go really high, or slag can go really, really high. But these are just different materials and they perform like vastly different. And so with SCMs, it's just like be really careful and take a little time and explore, you know, what that material is, what it should be used for. And as Kelly said in the very beginning of this, test batches, trial patches, that's the way to really learn about these materials. Chapter 7 is about mineral fillers, which are very similar to SCMs, where you replace some of the Portland cement with a mineral filler. But these materials are largely considered to be inert. There's a lot of information out there now saying, well, maybe they're not totally inert, maybe they kind of interact in different ways with the reaction. I won't get into that now, but largely they play a bit of a different role than SCMs. So in the picture here on the left is silica fume, and then on the right is silica flour. And so they're both made of silica and oxygen. They're both, you know, fine materials, although silica fume is like super, super fine. It doesn't look like it, but it really is. But these are totally different. Silica fume is super, super reactive. Silica flour is largely inert. And so you can't just go on particle size. You can't just go on composition. You have to go, in this case, on what is the structure, right? What is the chemical structure of these materials, where silica fume is glassy and silica flour is crystalline. And so within the chapters 6 and 7, we really tried to just sort of highlight some of those differences and make it clear that these materials are all different. And so we go through each of these materials. Ground limestone, of course, is the most common of mineral fillers right now. Moving on to chapter 8. So this is the chapter that is about, that deals with sort of what can be done at the plant, what can be done at the cement plant. And so what we did here was try to do two different versions, sort of a traditional ASTM C150 plant. And I'm not knocking that at all. Amazing stuff. Portland cement, I love Portland cement. I think it's really great. I just think that it's there's a lot of things we can do with Portland cement to create a lower carbon industry. So this is just sort of considering a couple kind of inputs and outputs from a traditional plant versus maybe a lower carbon plant that's making the same material, but just differently, processed differently. So for example, you could get your electricity from the grid, which might be normally fossil fuels, and you could maybe change to renewables. You could use virgin raw materials here, like limestone, or alternative raw materials, something that's decarbonized already, that doesn't have the carbon in it already, or some biogenic calcium carbonate, or there's a whole bunch of really cool different materials for the alternative raw materials. Fossil fuels to heat the kiln, you could use alternative fuels like biomass. Waste heat is usually actually captured. That's probably not fair to put that as just leaving, but we could really make sure that we utilize all that waste heat. So the kiln's cranking out a lot of heat, right? And with the flue gases, you end up losing a lot of heat if you don't capture it. And then the big one a lot of people are talking about is traditionally those CO2 emissions just go out the stack with the flue gases. And in some of the newer plants, or sort of, they're looking at trying to capture that carbon and actually utilize it. And so we call that CCUS, carbon capture, utilization, and storage. And I'll mention that in just one moment. All right. So thinking about what's going on at the plant, okay, you can kind of think about it, that cement, that Portland cement, in two different ways. So think about it in terms of clinker factor, okay, which means how much clinker is in your concrete, okay? And remember, clinker are those little nodules that came out of the kiln, okay? You can also consider clinker carbon intensity, meaning to make that clinker, how much carbon went into making that clinker, okay? And so if we start out here where we have a high clinker factor and a high clinker carbon intensity, we have traditionally produced Portland cement, okay? So that was the gray one at the top on the last slide. If you go to the left here, okay, and you reduce your clinker carbon intensity, that means you're dealing with a lower carbon Portland cement. So you still have clinker, there's still clinker, but it was made maybe using alternative fuels or alternative materials. If you go down, now we're saying let's reduce the clinker content, okay? And so we say, I'm going to use traditional Portland cement, but I'm going to put in some SCMs or some mineral fillers, okay? And so that's the option. And then the third, or the other option, is you can kind of do both. And you can say, okay, I'm going to use a lower carbon cement, and I'm going to blend it with fly ash or slag or some other material. And so you can kind of maximize that. And so some of these can be kind of compounded on top of each other. So something to just consider. And again, this is not something that you or I have, unless you're a cement producer, I guess, watching this, but have control over. And, you know, there's fairly significant cost and investment in a lot of these, but it is something that's coming down the pike. All right, so CCUS, carbon capture, utilization, and storage. So you hear that a lot. We tried to break it down and make it kind of clear what's going on with regard specifically to the concrete industry. So carbon capture means that we're capturing the CO2 from the production of the Portland cement. And that could be directly captured, it could be in the flue gas. There's a whole bunch of really cool technologies out there on how to capture the carbon. Now, once it's captured, okay, you can utilize it in a whole bunch of different concrete products. So one of the ways that so you're essentially like, you're sort of like smashing the carbon into the concrete itself, okay? Because one cool thing about concrete is that it actually does absorb some level of carbon dioxide over time. Like if you have a sidewalk in front of your house that's exposed to the atmosphere, it really is actually pulling in some of that CO2. It's just doing it really slowly and not a super ton. It kind of depends on surface area. And so some of these methods here are trying to really accelerate how much carbon can be kind of pushed into the concrete. So sometimes they inject it into fresh concrete in the mixer. Sometimes they cure precast concrete in a carbon-rich environment, and you can make aggregate, SCMs, mineral fillers. You can even pump CO2 into water to dissolve some of the solids that come from the water that you use from cleaning your truck. So there's all sorts of different technologies people are looking at, saying, how do we use that carbon? So that's US in about 30 seconds. That is definitely a consideration, something that's being talked about a ton. Okay, so keeping moving on with those things that can be done at the plant. One of them is, the second one is this concept of blended cements. Okay, so blended cement is when you use fly ash or slag or something that you would sort of include at a ready mix plant. But instead of doing it at the plant and saying, I'm going to put 500 pounds of cement in and 100 pounds of fly ash in, you buy it like pre-mixed from the cement plant. And so there's a whole bunch of different blended cements out there, but two that we specifically look at in this document are Portland limestone cement, or type 1L, and which is Portland cement. It just has like an additional amount of limestone in it. So here you can, I didn't put a label on this, I'm sorry, but this is percent limestone out of the total mass of your Portland cement. ASTM C150, which is the standard specification for Portland cement, allows up to 5%. And ASTM C595, which is a blended cement spec, allows between 5 and 15%, so you can really up that limestone content. And type 1L cement is more popular, or not popular, but it's used more often than Portland cement. And then if you designate and say, I want to type 1L10, that's like 10%, you're allowed to kind of go plus or minus 2.5% on either side of that. Here's a picture. It's a cool SCM image from Dale Bentz from NIST. Thanks, Dale. And thanks to everyone that gave pictures to this guide. I think that I really enjoyed getting all the pictures, actually, and looking at all of them. But this is showing a high, the blue is limestone, showing a high blended cement with a high amount of limestone. And like I think it was like 50% or 40%. And a lot of folks in like Europe and around the world are kind of investigating, and the US are investigating, like, can we really bump up the mineral fillers? So the mineral fillers are something to really keep an eye on going forward. Another one of the blended cements that is getting a ton of attention is LC3, which stands for limestone calcined clay cement. And this is a picture of a test section at Minroad, which is in Minnesota, shout out Minnesota, where they're testing it. And so LC3 cement is by Karen Scribner and her team. And it's really cool. What they did is they just looked at all of the SCMs out there and the mineral fillers, and they said, what are the most available? And they said, well, limestone and clay are the most available, like, globally. And so they developed a cement around that. And so here you can kind of see this is like the breakdown by mass of Portland cement. So you can see it's like 90% Portland cement, some gypsum, and some limestone. PLC, which we just talked about, allows you to increase that limestone. And then LC3 said, okay, we're going to put like half, and there's a bunch of different formulations, but we put like half Portland cement. We're going to max some gypsum. We're going to max out our limestone, and then we're going to put in calcined clay, which is clay that's been heat treated. And so that's a big one right now. So there's a section on that. All right, chapter 9, concluding part 2, is about alternative cements. And this is kind of cool. It's like a bench kind of in Belgium, I think. This picture is from John Provis. This is alkali activated cement. And it's kind of funny, but I actually, in asking for pictures, I actually got like a surprising number of pictures of concrete furniture. So here's another one. It's a bench from Maria Younger. Thank you. So it's kind of funny. Anyway, I got more too, but I didn't put them in here. But anyway, it's a big deal, I guess, to do furniture. But for alternative cements, there's a ton of them out there. The chemistry varies. And there's, many different ways to sort of organize them. The way that we did was we said hydraulic alternative cements, alkali activated cements. Hydraulic alternative cements are those that can be activated with water, similar to Portland cement where you just add water. Alkali activated cements are activated with a high pH activator. There's magnesium-based cements, and then there's carbonated cements, which are specifically designed to be cured in an accelerated carbon curing environment. So in summary, sort of, one of the things that we would frequently hear about from folks that were maybe not as familiar with concrete, but maybe in a position to make some big decisions, was like a kind of confusion on SCMs versus alternative cements versus, what's what. And so we really tried to make it sort of clear that, while these materials all sort of swirl around, there really are specific efforts made toward, okay, replace some of the Portland cement, make this Portland cement differently, or just get rid of the Portland cement. And so this chart is an example of how we tried to show that. I'll just go through it for a moment here. But in the dark gray at the top, that's your traditional ASTM C150 Portland cement. In the lighter gray, that's the low carbon cement. So they're the same material, but they're just made differently. Their carbon intensity is different. And then going down, when you see this hatched or diagonally hatched dark gray, light gray, that just means you could use either, okay? And so you could do SCM mineral filler addition during batching. So that's at the ready mix plant, and that could be slag, fly ash, glass, any other material. And then there's all these blended cements, okay, which are in this kind of category here. And you can see there's limestone, slag, pozzolan, which could include fly ash or glass. And then you have a ternary blend where you use 3 at one time, okay? And these they're not interchangeable, right? They're not just like totally interchangeable. You have to really know what material you're using, but the replacement levels can vary significantly. And then we threw in LC3 here just to show that. And then you can see alternative cement, there's no gray at all, just totally getting rid of Portland cement, though sometimes there's a tiny bit in, but it's usually pretty much gone, okay? So again, we try to just make a lot of charts and stuff like this to try to help kind of organize these concepts. Okay, so part 3, like I said, we went through, the binder in part 2. Now we're saying, okay, what else is there? And, you might think back to that chart I showed really early where it said the Portland cement had this really high carbon footprint, and it does compared to like water and aggregate. Well, they still matter though, right? They still, every little bit helps. And so this chapter was looking at aggregates, chapter 10. So here's a picture of some Lake Superior stones I couldn't resist from the Keweenaw. And we broke down the aggregate options into recycled aggregates, industrial byproduct aggregates, and then carbon sequestering aggregates. And so you have your recycled concrete aggregate, glass, plastic aggregate, bunch of slags, right, in the industrial byproduct aggregates. And then the ones that can be used that are kind of aimed at sort of sequestering some CO2 within them. And throughout the book too, I think there's confusion because you say, well, here's blast furnace slag. I thought blast furnace slag was an SCM. Well, it can be used as both depending on some different factors. And so we tried to really point out where we could, where one material can be used in multiple places. Because I think that causes a lot of confusion. So here's some recycled concrete aggregate up here, just kind of a cool aggregate processing picture. And then I put this boat down here showing transportation to remind myself to say that at the beginning of the aggregate reinforcement and water chapter, we tried to provide a baseline. So what is kind of like the traditional type of aggregate that's used? And again, this depends on where you are geographically, of course, but just sort of a generic, here's the run-of-the-mill aggregate. And then what are the contributors to carbon for that run-of-the-mill aggregate so that you can sort of say, well, how can we tweak those and reduce them? Okay, and so there's a whole section in each of those chapters sort of outlining that, and then it goes through sort of what are the levers that can be pulled to change, to reduce that carbon, and then also what are the alternative materials that can be used. Similarly, for the reinforcement chapter, we went through, and the standard that we took was a classic blast furnace steel rebar, okay? And then we go through and say there are other low carbon production routes to make steel, right? There's electric arc furnace production where you're using scrap steel, etc. So we kind of go through those. Again, that's sort of maybe more of a buying power if you're sort of aware of how things are produced. And then you can look at an EPD, you can get an idea of what is that embodied carbon. We talk about structural efficiency, we wanted to introduce pre-stressing steel, high-strength steel, include those because they do play a role in low carbon concrete. And I'm sure any of you in the area know, or geez, anywhere in life, there's always things that blend together and kind of cross boundaries. And so we tried to stick to materials, but we had to acknowledge in many cases that there's lots of other decisions that impact low carbon concrete. We have a section on corrosion resistant rebars. And so again, this would be a good example of like the downstream savings where maybe you choose a material that maybe isn't the lowest embodied carbon up front, but it has a kind of an added corrosion resistance to it so that later on during that use phase of when you're actually using the concrete, it might be a lot tougher, resistant to corrosion, and that means less maintenance or replacement. We looked at FRPs, a whole bunch of different FRPs. We did a bunch of fibers, specifically steel, synthetic, and glass. And then we did a section, we kind of pulled all the bio-based natural reinforcements into its own section. And so discussed those there. And I should preface this with that I am absolutely not an expert in all of these areas. And so I appreciate everyone that was able to contribute to all of these different sections and review this document. So here's a picture of some of the materials that we looked at. And we did try to include pictures where we could just to help kind of give an idea. A bunch of different types of fibers. Here's a core of UHPC, ultra high performance concrete, which has steel fibers in it. You can see the cut cross section of the fibers. You can see kind of a nice dispersion there. This is glass, FRP. And then this is some epoxy coated rebar. So we tried to go through all that we could think of. For the water chapter, this is a picture of Lake Superior. Shout out Great Lakes. In the water chapter, this is a pretty small chapter actually, but we wanted to acknowledge that, of course, water is a material and it does impact the carbon footprint of concrete. So where is the water used in concrete? Talking about how do you reduce the water demand during mixing? What are some alternative water sources if water is not readily available to you? What are some water conscious construction practices? Again, that's sort of bleeding into construction practices, which is different than material selection, but it all goes hand in hand in the end. And then CO2 mineralization of processed water, which I had mentioned earlier with the CCUS. All right, so now on to chapter 4 or part 4. So we felt like we would be remiss if we didn't include chemical admixtures, but also just sort of an acknowledgement that just because you choose low carbon materials doesn't mean that you're going to necessarily have the lowest carbon concrete. And I sort of think of it like if you were going to make a homemade pizza and you made the dough, homemade dough, you made homemade sauce, you got really nice pepperoni, really nice cheese, and then you just put it all in a bowl and you mixed it together and you put it in the microwave. Oh man, you had these really great materials, but you didn't quite use them right? And so that's kind of where part 4 is saying there's like these really nice mixed design strategies, mixture proportioning that will enhance, the materials that you select that might have been low carbon materials. And so chapter 14 or 13 really focuses on chemical admixtures, specifically how they can help lower clinker content, so reduce the Portland cement in concrete, reduce the total paste volume, which we didn't really talk about that, but that would be like if you optimize your aggregate gradation, you can actually put less paste, and paste is water and cement together, into the concrete, which therefore lowers the clinker content. Design for durability is huge, and we do talk about this actually a lot more than I have talked about it in this presentation in the guide. And then improving construction efficiency and sort of how all of these different admixtures can help achieve those goals. And then chapter 14, again, these last 3 chapters are pretty short, but we wanted to acknowledge that there's some really interesting concretes out there that utilize a lot of these principles and ideas that we had talked about and materials that we talked about. And so on the left here, you can see that's ultra high performance concrete. If you're not familiar, it's really interesting stuff. There's no coarse aggregate. It has steel fibers, really strong, practically impermeable, really interesting stuff. Self-consolidating concrete here on the right. That, there's no segregation, but it's super fluid. And so it's able to get into the nooks and crannies and in high reinforcement areas. And so we looked at high performance concretes, construction efficiency concretes, which would be like the SEC, And then environment and system driven concretes, which we sort of just put like pervious concrete and some of the others into that category. And I think you could write a whole nother guide on chapter 13 and chapter 14 and all of these really. All right. So in summary, it was really uplifting to write this guide. And I have to give Sarika a huge shout out because Sarika put up with me for this took a bit longer than we anticipated. And she put up with me so much, and we had so many really great conversations talking about how best to explain things. And so Sarika, I hope that everyone knows how much she had to do with this guide. So thank you, Sarika. But it was really uplifting to look at all these different materials and all these different, so many people are working on this issue of trying to reduce the carbon footprint of concrete. And I think that it can happen. I think we've got to do life cycle thinking. We got to think big picture, make that the norm, right? Balanced decision making. It's complicated, yes, but you just have to consider a whole lot of things and make it not just like, oh, we just use this much cement and this much water, and that's how it's always been. Start really looking at how those decisions, all the different things that those decisions impact. Collaboration, of course, right? The more collaboration you can get on a project between the material producers, between the constructors, all the people, the engineers, everybody involved is just going to help improve the project. And then also, if you do have the option or the opportunity to explore some of these newer materials that are emerging or experimental and do a pilot project or something safe, of course. But the best way that these materials are going to move forward is for us to use them and to learn about them and to see how they exist in practice. So with that, I'd like to just close by saying that the goal of this guide, like I said, is just to help folks understand low carbon concrete. And the plan is to keep it updated, or not continuously probably, but frequently. And I think New is working on when that will happen. But if you do have ideas or information that you think would help the guide, please do contact New. And with that, I'd like to turn it back over and say thanks.
Thank you, Mary. We have about 5 minutes left, but we have some great questions from the audience. If we don't get to them, I would suggest, I think at the end there's some information, and feel free to reach out to us. But I just wanted to ask a few questions of you to maybe give the folks here online an idea more. You hit the surface. This guide is very comprehensive. And what I do like about it is it is one place where all of this information is in one location. A lot of other great guides out there on implementation and things like that, but and you do refer to them in your guide. So, but one of the things I wanted to maybe have you answer is, you looked at all these different materials, all these different options. What in the guide, how much time did you spend on and allocate to looking at addressing performance, like the performance characteristics of some of these? So maybe you could share that with the audience.
Sure. Yeah, we address it throughout, and like you said, there was no way I could say everything that was in the guide in 50 minutes. But chapter 4 gives you, so that's the part 1, which is like the breakdown of the basics. That goes through what are the fresh properties you should consider, what are constructability issues, what are hardened properties you should consider, what are the ASTMs for all those tests. So if you're not familiar with performance, that's a good place just to start for basics. And then pretty much through every single material that we produced, that we talked about, we really tried to include how does this impact fresh properties and hardened properties of the concrete, and also how does that compare to the baseline, right? So if you're using regular blast furnace, steel reinforcement, and now you're using a GFRP, glass fiber reinforced polymer, how does that change, or what kind of things could you expect? And we did try to put a ton of references into especially other ACI reports, because there's so many really in-depth reports on all of these materials that really focus in on the performance. And so, yeah, I probably didn't mention it as much as I should have, but it's a significant part of the book, of the guide.
Yeah, and I just wanted to, I guess, give you the opportunity to say that, because when you do look at the guide and go into each of the details of these chapters, I think that's a key thing. Sarika, we had a couple questions. Did you want to field maybe another one of them from the audience?
Sure. Thanks, Mary, again. Great presentation. We have more than 10 questions at the moment. Let's see. Again, we can answer these via emails if we don't have time.
Yeah.
I think you discussed this, Mary. Curious if carbonation fall in the concrete carbon life cycle model.
The concrete, if
Carbonation fall in the concrete carbon life cycle model. I mean, you have even provided pictures in the guide.
yeah, we do discuss carbonation a fair bit. And so there's a really cool diagram, which I didn't put in, of course. It was from a document by Scrivener that we sort of adapted to our guide, but looking at the sort of the carbon cycle of concrete, right, where you start with typically like a limestone, which is calcium carbonate, and then you put that into the kiln and you have calcination. So the CO2 goes into the atmosphere, right? And then you hydrate your cement, you mix it with water, right? And so now you're sort of creating these phases that are open to carbonation later, which is when those phases react with the CO2 in the atmosphere to pull the CO2 back in, right? And so it's sort of a cycle. And so it is discussed pretty, we do have a pretty decent chunk discussing that. And then it also is discussed within the CCUS section as well, sort of how how does that CO2 get put back into the concrete? Because there's a lot of phases they sort of revert back to calcium carbonate in many cases. So is that what you were asking, or?
Yeah, and I think too, Mary, I mean, one of the things that the guide shows out is it goes through the life cycle stages. And right now in North America, I mean, we look at stages A1 and A3. We're not looking at all of the stages. So,
Right.
but it's a good explanation, the carbonation, how important it is in the whole life cycle and how we need to move forward with addressing that. And I think there's a lot of research and a lot of people gathering data and how that best can be used. But I think the guide, from the question, what we can say is, yes, it's addressed in the guide and we educate people on it. And we definitely love to add carbonation into the life cycle of concrete moving forward. So great.
Definitely.
Great question. Another question that I saw from in there was related to electric arc furnace slag addressed and in the aggregate section. And I think yes, it does. There is a table that talks about it. Again, we address a lot of the materials, Mary, and if you want to add some more, and the idea is to make people aware of it and then guide them to where more information is on it. So Mary, I don't know if you have anything more you want to add, how you address some of these materials within the aggregate section, specifically electric arc furnace.
Sure. Yeah. So we tried to, like I said, get our arms around all the, materials that we could find. And so I think the question probably is pertaining to the fact that slag that comes from a blast furnace, like a BOF, basic oxygen furnace, I think that's sort of the traditional method. You get this slag or slag cement, which is very commonly used in the industry. And that the blast furnace is what's used to make the iron, right? Which is used to make the steel, which is used to make the reinforcement. And so there's a lot of switching going on, or kind of transitioning over to EAF, which is electric arc furnace, which is a different way to produce steel. And so a lot of there's still some raw materials that go into that usually, but there's a large portion of recycled steel that goes into it as well. And so you can imagine that, reduces the embodied carbon, but this slag is different. The slag is a different product. And so it's a really good question. I don't know. I'm trying to think now if we really did address that full on, but if we didn't fully, I think there's sort of a, mention that the methodology of the production does impact the composition of the slag. But that's a good point that we should make sure that is definitely in there to address EAF slag specifically.
Yeah,
so
and that's emerging. Yeah, it is some of that
definitely
item. So
that's a big consideration.
well, Mary, we're heading towards the end of the hour here, so we're gonna wrap up the questions. But again, we'll try to reach out to those that we have your information to address that. Take a look at the guide. It's very comprehensive. There's a lot more information than what Mary had time to go over. So again, we thank everybody on behalf of NEW, and thanks to Mary and Sarika. And I think Kelly has some parting information for the folks here online. So thank you again for participating today.
Okay, thank you again, Mary. That was a great presentation, a lot of information. I appreciate it. Just a few words to wrap up. Please visit the new website at newconcrete.org for resources on lower carbon concrete production and placement. The website provides access to our sustainable concrete guides, frequently asked questions, webinar recordings, and more. You can see on this slide here, the QR code shown will take you to the ACI bookstore and where you can purchase the news recently released guide. And please join us for the next upcoming webinar. Mary, if you can move it to one slide beyond this, we have a webinar coming up on February 26th, presented by Nathan Forrest on ACI code 323, low carbon concrete, real world implementation and examples. So please register for that. It'll be a great webinar. And we do appreciate your time today. Thank you for attending, and please stay tuned for more webinars, monthly webinars by New. Thank you again.